Okay, let's continue with our discussion of limits. And the function that I want to look at this time is the following. Let's look at g of x equal to 1 over x squared. All right? Now, we know that the graph of this function looks a little like the following. It has an asymptote along the y-axis at x equals 0. It's positive valued, and it also has an asymptote along the x-axis as the values of x go to plus or minus infinity. In other words, as they get larger and larger. So we have the y-axis is a vertical asymptote, and the x-axis is a horizontal asymptote. All right. Notice also the domain of g of x is the set of all real numbers without 0, x equals 0. So this is equal to minus infinity to 0, union, again, the open interval from 0 to plus infinity. So 0 is excluded. Which makes sense because I can't divide 0 into 1. All right. Nevertheless, we can ask the question, hey, what is the limit as x goes to 0 from the left-hand side of g of x? Okay, remember what we said. We said that this limit is going to be equal to some number L if the values of g of x get closer and closer and closer to L as x gets closer and closer to 0 from the left-hand side. So we're letting x approach 0 from the left-hand side. But what happens to the values of g of x? The closer x gets to 0, the bigger the value of g of x. So those values of g of x get bigger and bigger without bound. So they actually tend to what we say plus infinity. So what we write here, so as x gets closer and closer to 0, notice it can never equal 0. And especially now because our function's undefined at x equals 0. As x gets closer and closer to 0, the values of g of x get larger and larger without bound. So what do I mean by that? I mean that if you give me some number m, I can find a value of x close enough to 0 such that 1 over x squared is bigger than n. So here I'm going to note that this means, this without bound means that given any real number m, and here we're thinking of a large real number, a large positive real number, we can find a value of x such that 1 over x squared is greater than m. And that certainly makes sense. This is equivalent to writing that x squared is less than 1 over m, or x is less than 1 over the square root of m. Okay, so for any value of x less than 1 over the square root of m, 1 over x squared is greater than m. So all those, here's 0, here's 1 over the square root of m, and for any value of x between these two points, 1 over the square root of m and 0, 1 over x squared is greater than m. If this happens to be the case, then the graph of our function has a vertical asymptote at the point, as this does at x equals 0. And we write in this case that the limit as x approaches 0 from the left of g of x, which is equal to the limit as x goes to 0 from the left of 1 over x squared, because g of x is equal to 1 over x squared, is equal to, now since this is increasing without bound, it keeps on getting bigger and bigger, as big as I can possibly want to make it, we write that this is equal to plus infinity. Okay, and so this is usually the case when we have an asymptote at the point where we're letting x approach the value. And here it's 0. Also, the same thing happens if I let x approach 0 from the right-hand side. This is also equal to plus infinity. Okay. Now, we can look at the following. Let's call it h of x equal to 1 over x. In this case, what do we know? We know that we have a vertical asymptote in the positive x direction for values of x greater than 0. And for values of x less than 0, 1 over x is going to be negative. And so our graph is going to have an asymptote along the y-axis. I think, did I say the x-axis? I meant to say the y-axis. So we have a vertical asymptote along the y-axis in the negative direction for values of x less than 0. So here's our graph. And now what we can write is this. Well, the limit as x approaches 0 from the right of h of x, this is going to be plus infinity, okay? Because we have our asymptote along the y-axis is in the positive direction for values of x that lie to the right of x equals 0. But then things change a little bit. When x approaches 0 from the left-hand side, the values of h of x get smaller and smaller. All right, they're becoming more and more negative, and so we write here that this limit is equal to minus infinity. And here we have an asymptote. The graph of our function h has an asymptote along the y-axis in the negative direction for values of x less than 0. And that's reflected in the fact that this limit happens to be negative infinity. Okay? Now, of course, these two limits are not equal to one another, so we would say that the limit as x approaches 0 of h of x does not exist. So now we have two separate cases where we find that the limits of our function at a particular point do not exist. One is where we have this finite jump discontinuity. Another one is where we have this vertical asymptotic behavior at the point where x is approaching our value. There's a third type, and it's this. Suppose I have a function let's call it f of x, equal to, let's say, the sine of 1 over x. Okay, and suppose I look at the limit as x goes to 0 from the right of the function f of x. Well, let's look at some values. So let's think about, hey, x equal to let me think, 1 over pi, 1 over 2 pi, 1 over 3 pi, 1 over 4 pi, 1 over 5 pi, and so on. So what's happening to these values of x? Well, they're getting smaller and smaller. They're all positive. They're getting smaller and smaller, so they're approaching 0. And they're approaching 0 from the right-hand side. Now, let's compute. So the sine of 1 over pi is equal to the sine of pi, and that we know is equal to 0. And then I have the sine of 1 over 2 pi. This is equal to the sine of 2 pi, and this is equal to 0. And in point of fact, the sine of 1 over x, where x happens to be any one of these values here, is certainly going to be 0. So we would perhaps imagine that, well, this limit here, this limit of our function f of x, which happens to be the sine of 1 over x, that this limit might be 0. But let's change things up a little bit. Now let's look at the following. Let's look at the following values of x. So I'm going to take x equal to 1 over pi divided by 2, 1 over pi divided by 3, 1 over pi divided by 4, 1 over pi divided by not 5. Let me erase these values. Sorry. Let me redo that. So what do I want? Sorry, I didn't want that. I want the following. I want x equal to the following. 1 over pi over 2, 1 over 3 pi over 2, 1 over 5 pi over 2, 1 over 7 pi over 2, and so on. Okay? Now, these values, they also approach 0, so these get closer and closer to 0 from the right-hand side. Okay, and if I look at the sine of 1 over pi over 2, this is equal to the sine of pi over 2, which is equal to 1. And if I look at the sine of 1 divided by 3, 1 divided by 1 over 3 pi divided by 2. This is equal to the sine of 3 pi over 2, and that's also equal to 1. And in point of fact, if I look at the sine of 1 over x, where x happens to be one of these values, then this sine is going to equal 1. Okay, so now what would I say? I'd say, well, now the limit as x goes to 0, if it's going to 0 through these numbers, that limit is going to give me 1. Well, I can't have both. The sine, so if the limit's going to exist, it has to approach just one value, a unique value. And here we have a situation where if I let x equal these numbers, which are getting closer and closer to 0, the sine is going to give me 0, so the limit would be 0. Whereas if I look at this sequence of numbers here, which these numbers are getting closer and closer to 0 from the right-hand side, then when I evaluate the sine of 1 over x at any of these numbers, I get 1. So I would think my limit should be 1. In this case, the limit of the sine of 1 over x as x goes to 0 from the right-hand side, this does not exist. And in point of fact, what you can show is that the graph of this function looks something like this. Goes a little like this. It keeps on oscillating infinitely often in here, okay? So in other words, the sine, as x gets closer and closer to 0, the sine can be made to get closer and closer to any number between -1 and 1. And in that case, the limit does not exist because it's not going to be unique. Let's take a look at one of the problems in the book. This is problem 28. They want you to look at the limit as x goes to 0 of 1 over 1 plus e to the 1 over x. Okay? So what I'm going to do is I'm going to set y equal to 1 over x. Now, what happens to y as x goes to 0? So I'm looking at the limit as x goes to 0 of 1 over x. Well, what do I know? So as x goes to 0, what happens to y? Y is going to go to, and here what I should do is make this a plus sign here. Okay, I'll make this a plus sign. Then as x goes to 0, from the right, we know that y is going to go to plus infinity because y is equal to 1 over x. X is positive. It's going to 0 from the right-hand side. And so I have that that this limit is equal to plus infinity. All right. So this means as x approaches 0 from the right, y approaches plus infinity. So I can write this limit. The limit as x goes to 0 from the right of 1 over 1 plus e to the 1 over x. I can write this as the limit as y goes to plus infinity of 1 over 1 plus e to the y power. Now, what do we know? What happens to 1 plus e to the y as y goes to plus infinity? Well, this certainly goes to plus infinity as y goes to plus infinity. Okay? Because we know the exponential function blows up. It gets bigger and bigger very quickly as the values of its argument get larger and larger. All right, so now this is equal to, this is equal to 1 divided by a number that's getting larger and larger as y goes to plus infinity. So this is going to 0. Okay. Now, let's wait. Okay. So what happens as x goes to 0 from the left? So we're looking at 1 over x. Well, we know this is equal to minus infinity, right? That's what we did above. So as x goes to 0 from the left-hand side, y goes to minus infinity. So I can write the following. The limit as x goes to 0 from the left of 1 over 1 plus e to the 1 over x, this is equal to the limit as y goes to minus infinity of 1 over 1 plus e to the y. Now, remember, the exponential function has a graph that looks like this. Here's my x-axis. So as x goes to minus infinity, e to the x goes to 0. As y goes to minus infinity, e to the y is going to go to 0. So this is just equal to 1 divided by 1 plus 0, and that's 1. So what we have is the limit as x goes to 0 from the right, that's equal to 0. The limit as x goes to 0 from the left, that's equal to 1. So that tells me that the limit as x goes to 0 of 1 over 1 plus e to the 1 over x does not exist. Okay. All right. Look at some of the suggested homework problems in this chapter, and we'll continue our discussion of limits on Wednesday.